Broadcast is now starting. All attendees are in listen-only mode.
Okay, good afternoon, everybody, and this is Dr. Mansour, and this is the Civil AM free webinar or a free workshop. And today, I believe, today at lunchtime, I emailed you something. I hope you got it. Mini exam number 5, I believe, if my numbering system is correct. Today is a 4/18, so Saturday. So the one I sent to you is this one here. some problems related to materials. And materials, as all of you know, is based on the NCEES. It does have a lot of questions, and let me get my book here, show you what I have in my book. And basically, the AM portion, let me get the NCEES very quick. Here it is. Materials. Let me switch to the camera because it seems to me I lost the camera somewhere. Yeah, I lost it. Let me bring it. So if you look to the NCEES, you will find that they have, under materials, you will find they have these topics and the percentage or the number of questions that related to this materials section. First one is soil classification and boring log interpretation. Soil properties like strength, permeability, compressibility, phase relationships, concrete, reinforced and non-reinforced, structure steel, material test methods and specification conformance, and finally compaction. So those are the topics that listed under NCEES, and they have 6 problems or 6 questions out of 40 questions, as you know. So we need to make sure that we really understand the topic. And so I did not include problems about soil classification. I will be glad to go over that. So the I believe one of you was trying to contact me while I'm teaching the class. It is if you go to our website, you will be able to do it. I don't know. I haven't received the invite today. You don't have to receive the invite. You can just join me. So some of you text me, and I cannot really answer every text because I receive. Okay, so I really appreciate if you can do your best, and since I hope that all of you join me, and basically the ID is available on our website, and also the link where you can go directly and enroll. And since you enrolled once, you're supposed to be joining me without any problem. Even if you did not receive a notification from the webinar company, you're supposed to be able to join me. So so do your best, and I will do my best. But some of you were texting me. I don't know if they were able to join me or not. But too many webinars. Yeah, I'm trying to answer them. Forgive me for that. Yes. Okay. So the question that I included this morning related to soils and concrete, and even some I injected from time to time some questions related to the this was emailed this afternoon. If you did not receive it, try to print it as we speak here, so at least to save time. So if your email, if this is the first time, obviously we don't know your email. If this is the first time you join us, Muhammad probably did not receive it, but after I finish, I will send it again one more time. Since you joined us, so your email address will be with us, and I will be glad to send it to you. Okay. So question number 15, for example, and I will try to be slow as I can. Said that it is 8 by 12 billboard is subjected to a lateral wind, not wing, wind load of 90 pounds per square foot. So there is a wind load, W, we use for wind, 90 pounds per square foot. The billboard is protected, okay, against overturning by two diagonal braces. They are spaced at 6 feet on center. And the brace is at 4 feet from the top, because this is 12 feet, and this is the 8 feet total. And I have couple braces, one here and one here. They are 6 feet on center. And he would like to find the force in the brace. Force, the axial force in the brace. So a 3D picture, I believe I have in my book, an illustration about that. And the picture that it might help us, or it will help us, in fact. In my book here, let me see, in chapter 2, I believe, under means and methods, there was a picture. Let me see if I can find it very quick. If not, I will. Yeah, here it is. Something like that. This is a masonry, CMU, masonry wall. And the masonry wall, because of the strength of the mortar and the wall in general, so we put some braces. This is a lateral brace. A brace is supporting the wall here and supported at the ground, or to the ground here. And this is the distance between two braces. So they are spaced such that they will be capable to resist any wind, because while the wall is still in gaining its strength, we need to provide some kind of support in order to. So if you take this picture here and try to draw it at the 3D, so I have a billboard, and there are a couple of braces. They are supporting this wall from overturning, one here and one here. And the distance between them is 6 feet, according to the problem statement. And the 3 feet here and 6 feet here, and 3 feet to the end. And he said that this distance is 4 feet, and they are supported at 4 feet from the bottom of the wall, of the billboard, sorry. And this is total is 12 feet, the total length. And here is 8 feet. So he would like to find the force, how much the force in each brace, the force. He called it T. It could be F, by the way, is a compression force, F or P, whatever he called it. And this is very similar to a problem, I believe, but one of you sent it to me this way. I translated it into English. And he would like to find the force in the brace, assuming that support at the bottom of the billboard is considered a hinge. This statement is very important because if you look to this, this is a vertical billboard, and this is the support, and this is the ground. The reason that this statement is mentioned here because we know as supports, there are 3 types of supports. We are interested here. It is hinge / pin, which is we draw it like this. And this has 2 unknowns. It has vertical, so A sub y and A sub x, for example, if this end A. Hinge, like the hinge in the door of your house. It has 2 components, but has no moment. The moment you can open and close the door because the hinges, except the friction we ignore it. The other one is a roller support, and we draw it like this. And the roller support has only one reaction perpendicular to the contact surface, if this is A. So I have A sub y, and this is like this. And the third type of support that you might see on the exam is a fixed. And the fixed is like this, totally fixed, either horizontally or vertically. Could be a wall, or it could be a beam. And for the fixed end or the fixed end condition, we have 3 unknowns. We have horizontal and vertical, and we have what's known as a moment, fixed in moment. It depends on the direction. So if this is A, I have A sub y, and I have A sub x, and I have the moment at A, MA, moment at A. Those are the 3 important supports that, plus the link which is an axial force along the member. So by looking to this problem here, and look to the free body diagram that I can draw for this scenario, I have a billboard. And this is the original ground, OG. And here is the brace that it is supporting this billboard 4 feet from the bottom, or from the top, because the entire height is 4 feet, 8 feet, sorry. And there is a wind coming this way. This wind, it is 90 pounds per square foot, 90 psf. And this is from here to here is 4 feet, also is given to you as 4 feet. and I need to get the force. This force here, F. This is a compression member, by the way. So the arrow is going into the joints, as we indicated when we talked about trusses. So if this support here is fixed, if the billboard with the ground is fixed, I have three unknowns here. So if this is the case, I have one, assume it's fixed first, two, and I have a moment. So how many unknowns I have if this is fixed? I have four unknowns. And this is a 2D system. Excuse me. A 2D system has the three available equations. The sigma force X and sigma force Y and sigma moment equals 0, equals 0, equals 0. So I have three available equations and four unknowns. This make 4 greater than 3. So this is statically indeterminate to the first degree if this end here is fixed. But in order to make my life easy, because statically indeterminate, this is statically indeterminate to the first degree. Which you cannot solve it unless you know the methods for statically indeterminate structures, which you are not required to know that for the AM. First degree, because 4 minus 3 is 1. So in order to convert the problem to make it statically determinate, they told us, or the problem stated that this here at the bottom is not going to be a fixed. It's going to be a hinge. A hinge is like this. You see? So right now, the problem is completely different now, and we can solve it. Because I have the brace is here. And right now I have only two unknowns at the hinge because there is no moment. Moment is equal 0. So I have only two unknowns here. F sub y and F sub x. Two components at any hinge. Here it is. A sub y, one in the y direction, one in the x direction. And I have the force along the brace, F or B or T, whatever you like to call it. So right now I have 1, 2, 3, three unknowns, three equations. Bingo. It is solvable. So it is aesthetically determinate, and I can solve it by applying the equation of, or the equations of equilibrium. We need to pay attention to every single word given in the problem statement because this is something very, very important. So the second step after that is to calculate the force Okay, my friend. Okay, some of you already give me the answer. Let's see if we're getting the same number as he suggested. So in this case, we will take the the distributed load that acting on the billboard and converted to at this level. At this level, it's not a big deal. The height of the, so this is 4 feet and this is 4 feet. So I have a distributed load given to me at 90 pounds per square foot. One of the rules, normally I needed to remember that any distributed load, two rules, in fact, two rules for the loads, I needed to remember them, that any distributed load converted to a concentrated load this is number one. Any distributed load should be replaced by a concentrated load or loads. This is the rule number one. So I have here a distributed load of 90 pounds per square foot, 90 pounds per foot square. So I need to replace this with a single concentrated load. And it will act at the middle, at the centroid. This is a simple load, uniform. So I have a load P. And this load P is going to be calculated as follows. 90, and units are very important, 90 pounds per square foot. I have the height here, which is 8 feet. But this brace, as illustrated here in the 3D picture, that I have two braces. We have something attributes called the tributary width. Tributary width. Or for frames, for diaphragms, we use tributary area. Here, this brace and this brace, they are a part of 6 feet. That means that each one of them is going to carry 3 feet. So 3 feet from here, and this 3 feet from here. That means that each brace is responsible for 6 feet. And I will modify the problem and show to you what will be the situation if the problem is modified. So I need to multiply now the 8 feet, the 90 by the height, which is 8 feet, times the responsibility, which is a tributary width, which is 6. 3 from each end. This will give you the total load acting at the centroid, at centroid C. So in this case, it is 90, enter, 8 times, 6 times. So it is 4320 pounds. Total load. Acting at the centroid is 4 feet away from the bottom. Right now I have two unknowns here. I have A sub y, let me call this is A, and I have A sub x. Normally we draw it in the positive direction, and if we ended with negative, that means our directions are not correct. And I have the force, I call it F, for example. So I have sigma force X equals 0, sigma force Y equals 0, and sigma moment equals 0. Those are the three equilibrium equations for any 2D system exists on Earth. So the moment equation, which is the last equation here, is very powerful, because I could sum moment here, or I can sum moment about A. I will cancel A sub y and A sub x. The only left unknown for me is F. And I mentioned that there are two rules. We said that any distributed load should be replaced or substituted by a concentrated load or loads, or concentrated loads. This is rule number one. Rule number two, any inclined load or loads, if I have more than ones, must be resolved into components. What does it mean? It means that if I have a force like this, like F, along this brace, this is one brace. So moment is equal force times distance. By definition, the moment equation is defined as a force times distance. But this distance, we call it arm, or moment arm. This distance must be the perpendicular distance between the force and the point. I am summing moment. It must be the perpendicular distance. So in order to make life easy, I can sum moment here, but that means that I need to determine the perpendicular distance, this here. How much is this perpendicular distance? I don't know. Can we do it? Maybe. Why should I do that? Now I can eliminate this by resolving this force into two components. One horizontal and one vertical. This F I'm going to replace with two components. F sub x and F sub y. This is the easiest way. So if I have a force like this, I will call it, oh, this force has two components. F sub x and F sub y. And this is 4 feet and this is 4 feet. That means that this angle is 45 degrees. So the F sub x is equal F cosine 45 degrees, and F sub y is equal F. This cosine or sine, because they're the same in this case. Make it sine at least to stick with the rules. Sine and cosine 45 are essentially the same. So this F, the force F, I broke it down into two components, one horizontal and one vertical. Where is my, it was originally correct, here it is. F sine and cosine for 45 are the same, but let me give my space, self space here. So this is F, because this angle is 40, this is the angle theta, which is 45 degrees. So the force, it has a component in the x, which is F cosine, and this is F sine. Even when no sine and cosine for 45 degrees equal the same. And this is the rule that we learned in static, that any force F can be resolved into components if I know this angle theta. So this is F cosine theta, and this is F sine theta. This is gone right now, the force. I resolve it into two components. So please remember these two rules for forces, and this is true for all kinds of two rules for forces. So now I can go back again to the problem and apply this some moment here. So sigma moment about A equals 0. And I can say clockwise is positive. So I have this F sub x, which is F cosine 45 degrees, times the moment arm, which is 4 feet. And this is negative, because counterclockwise, plus P, which is 4320. The force times the moment arm, which is 4. So in this case, I can say F is equal to 4320 divided by, because 4 can cancel, divided by cosine 45 degrees. And if we do this math, you will get a number of 45 cosine inverted and multiply by 4320 times will give us about 6109.4 pounds. 6109. So probably, hopefully that we have an answer closer to this number. 6110, probably the answer C. This is if the two braces are equal distance from each edge. So the scenario might be, to make a little bit difficult, that he might make the braces are not symmetrical. That means one brace is carrying more for whatever reason or for the sake of the exam. He will make one brace here and another brace here. So he might say that this distance here is 3 feet, but this distance here is 5 feet, for whatever reason. And he gave you the distance here, for example, assuming this is 8 feet. Change the numbers a little bit. Normally, we prefer it to be symmetric like this, as far as the spacing. But for whatever reason, he might give you a scenario like this. So the same thing will be followed, except that when you take right now one, and he will tell you the maximum force. He will tell you the maximum force is this. In this case, he will not. So the maximum force in the bracing system is most nearly. And he will give you again 4 possible answers. In this case, we do have one brace, which is brace number 1, and this is brace number 2. This is the tributary width is still the same. So I will come here and I say this is 4 feet from each end, from each side, 4 feet and 4 feet. So the tributary width of this became 4 and 5 is 9. And this is just only 7 feet. So this is the most critical one. This is a critical brace. And in this case, when we do the calculate the force, you have to consider this. So when I calculate the force here, whatever the intensity of the wind, the height is the height, but this 6 feet will be different. The 6 feet came originally from 3 and 3 because he put 3 feet on from each end and 6 feet on center. So in this case, we can. So the problem can be modified such that he will give you a little bit different. And in this case, the maximum force is going to be the key here to select the most critical one, the most critical brace. The one is going to carry the largest, and this is something I need you to be aware of. Okay, so he might give you something else that instead of giving you the force, asking you for the force, he will give you the material. That this brace made of steel or aluminum or wood, whatever. And he will tell you what is the cross-sectional area, what is the cross-sectional area, assuming yield stress is equal to 32 KSI and a factor of safety of 3.0. So I can come up also with, this is another type of problems that I can take this problem here and can do it in two separate problems, one to calculate the force, and after that we can calculate the area, the cross-sectional area, if I know what is the yield stress and what is the factor of safety. So we know sigma is equal B over A. This is axial, because the force is axial, either tension or compression. In this case, due to this lateral load, which is a wind load, these members will be in compression. Okay, unless the wind came from the other side, it could be tension. So in this case, if I know sigma and I know P, I know the maximum force or maximum load, I can get the area. But this sigma here, in this case, is going to be, this is sigma allowable, the allowable stress, which is equal sigma yield divided by factor of safety. So I need to reduce the stress by the factor of safety. Okay, so I use allowable stress because he gave me something like this. If this is epsilon and this is sigma, so in this case, what he gave me the yield stress somewhere here, the F sub y, as we call it, or sigma sub y, it depends on the book. Okay. So the yield stress is given to be 32 KSI, but I'm not using the yield stress. I'm going to use something much, much smaller than that, which we'll call it allowable stress, sigma allowable. Like we did for the footing design, do you remember? Is equal sigma sub y or F sub y divided by the factor of safety. So this will bring the stress from here to here, just in case if the overload or the wind has been miscalculated. So I have factor of safety, I have reserve capacity for it. So please look to these things. All these are variations that could be part of a problem that you see it on the exam or something similar to that. Should we consider the eccentricity in this case? As far as what? Eccentricity of what? No, the eccentricity if the load is not uniform, but in this case the load is uniform. So here the eccentricity you're talking about, my friend, if the load is not acting along the centroidal axis. Let me make sure that I understand your question and correct me if I'm wrong. Okay. This is a uniform load, the wind. It will be acting at the center of the load. So the centroid. So in this case, this is a centroid C here, as far as the height. As far as this here, I will assume that the load, it is in the middle, because in this case, you are going to make the problem so complicated because it has the combined stresses. And this is something really going to be sigma, which is B over A plus or minus, a plus or minus MC over I. I don't expect that he will go to this far, but I will assume this axial and apply, in this case, the equation straight, because eccentricity, if the load, in this case, why eccentricity will occur? Eccentricity will occur if the load is off the centroidal axis of the member. This is the centroidal axis of the member, like that. And if the load is off center, like this P, this we call it eccentricity E. Okay, so in this case, we can replace this, as we explained in the class. I can replace this load by a force and a moment. And in this case, will give us what is known as a combined stresses. So if this is the centroidal axis, so in this case, I will come and add load P here and subtract load P here. And I still have the original P, which is eccentric load, and the distance E, which is eccentricity, still the same. So I did nothing as far as the equilibrium. I can replace this force, which is coming down, and this force is going up with a moment. So in this case, the final of this is going to be, let me draw it here, is going to be a combined stress where we have axial load plus, like the footing will solve a problem, by the way, I believe. So this is the centroidal axis of the member. So in this case, I have the axial load P plus the bending moment M, which is B times E. So in this case, yes, we have to apply this because the load is off center with respect to the member itself. Okay. I hope this is the answer to your question, my friend, or because I'm looking for the axial load, not for the bending. So please look at it and let me know if this is what. I understand that. Yes, I know that. Yes. So the second problem that I need to go over it. I don't know if you plot or you print all these problems. The aggregate, because I received a lot of questions about aggregates. And the adjustment for surface water. Problem number 8 is a good example for that. Water content, of course, aggregate used in a mixed design of concrete has been measured at 5%. The saturated surface dry water content is 1.5. By the way, I left some answers here to help you to make it easy. So the discussion I provided before related to this for about the fine aggregate and coarse aggregate and how can we adjust for the surface water. The adjustment for surface water. So the 3 circles I drew before in relation to the amount of the water in the aggregate, the SSD and the dry condition and the wet condition. And the moisture content as we define it, or we use a lowercase w, which is a moisture content. Moisture content is defined as the amount of the water, the weight of the water, divided by the weight of the solids, and normally expressed as this as a percent. And we determine the moisture content in relationship between the dry and the wet. So from here to here, I need you to remember that this is the moisture content. There is another moisture content that we need to pay attention to, which is the SSD, the saturated surface dry moisture content. From here to here, the SSD moisture content. The difference between this moisture content and this moisture, this is the total moisture content to bring, okay, the system from the wet condition, to completely dry condition, completely dry. here they might have some excess water on the surface if this is a piece of aggregate. So I might have all the pores filled with the water, and I might have some surface water. This is the wet condition. But for the SSD, the saturated surface dry condition, the situation is different. If this piece of the aggregate, let me draw another piece of aggregate here, hopefully. Okay. That means that only the internal holes or pores, as we call it, are filled with the water saturated, but the surface is dry. The surface is dry. And we determine this in the lab by putting the aggregate in the water for 24 hours, and next day we dry the surface. And after that, we weigh it and see how much water absorbed. So here, this is what is meant by the SSD, which is a saturated and surface dry condition. So this was what SSD. So the adjustment for surface water, we need to know this diagram, and we should know what is the moisture content and how much moisture is required to be absorbed by the fine and the coarse aggregates to reach the SSD. And this should be given to you into the problem statement, like the problem here, that he gave you that the moisture content or the water content is the moisture content, by the way. Moisture content or water content, they mean the same thing. 5%, but the saturated moisture content is 1.5%. That means that the difference between them is going to be the excess water or the extra water that should be subtracted from the mixture as far as a concept. So I need you to be aware of that the water needed for the mixing so don't forget this. The problem, I remember I solved a problem last week with the construction group, and there is no surface water adjustment because of the SSD condition. The aggregates were in the SSD condition, the saturate and surface dry condition. So I need you to be aware of that. So far, so good? Great. Okay. I have a question from, okay, so if I understand your question again, very difficult sometimes when the problem there was a wood at the top of the wall with concentrated loads. So two loads. If you can draw it for me, my friend, and tell me exactly what, because if I understood your question correctly, and correct me if I am wrong. Either let's go with this one here. So you are telling me that in addition to the distributed load, there was some kind of a concentrated load at the top. So in this case, if this is a scenario, so a concentrated, if the concentrated loads, I don't know how many of them. So the side view of this, and let me draw it. And again, I'm trying to imagine or visualize what you are telling me, and I hope that a question from, okay, you are telling me that whatever the angle of the brace, so in addition to this distributed load, could be wind or it could be seismic also, by the way. Seismic could be expressed as a lateral uniformly distributed load after we get the base shear. And you are telling me there is additional load at the top here, a concentrated load P, so this is W, and call this is F. And if this is the, I don't know how many of them along the entire length, it is two loads, and where they are located, these two loads, or three loads, or four loads, I really don't know. If this is F1, F2, F3, F4. Yeah, I try to draw a picture and send it to me. At least I can visualize exactly what you are talking about, at least to make sure that, because sometimes the question that you ask probably, or I cannot translate it. So I really appreciate if you translate into English. I will be glad to go over this. No, there is word on top. Means that if this is a cross section here like this, there is a piece of wood here. Um, please draw it and tell me exactly what, and I will try to visualize or try to come up with something that to match your thinking, and I'll be glad to come up with a problem or solve a problem, but I need to make sure that I really understand the question. Yeah. So this is something that the surface water is very, very important, and this is one of the tasks that we adjust the surface water based on this. And probably I can include, I have many problems to do that. So this is something that I need you to be aware of. Materials also related to the soil classification, which is very important subject. But let me go over before I leave the concrete. There are a couple of problems I included here. A problem number 23. Number 23, if you have it in front of you. He said that a beam 6x6 and 17.5-inch effective length is tested in the lab using the third point loading, and the breaking load or force is given, and he asks you what is the F sub C prime. So this is like a backward problem. And also, I believe one of you sent me this problem, so let me solve it to explain to you what. As you know, the concrete, this mixture of the 4 ingredients, define aggregate plus the coarse aggregate plus cement plus water. After we mix it, we test the concrete. And the testing that we do in the field or in the lab could be classified to the following. A fresh concrete, we test workability, either slump test or the Kelly ball, temperature, air content, how much air. All this done for a concrete while it is fresh, in the fresh condition. But when the concrete is hard concrete, so we test the cylinder to get the compressive strength, get the beam test, which is a modulus of rupture, which is a beam test, and another test is called the splitting test. Splitting test. All this given obviously in my book, which is coming from textbooks. I did not invent it. It's just the concrete. I have some pictures here. Let me see if I can locate them very quick. Here we go. So this is, for example, a picture of a slump test. This for a fresh concrete, wet concrete. We do the slump test. This cone, which is a 4-inch in diameter at the top, 8-inch at the bottom, and 12-inch in height. And we fill it in 3 equal layers, and we lift it up. And this is a true slump, where the concrete will come down this amount. How many inches is that? Inches. Based on the construction member or construction application, we can, there is a guideline given by the ACI code. This is called the slump contest. They came up with another test, is called Kelly ball, where we have this graduated scale and this hemispherical ball. We have concrete, okay, and we let the ball sit on these 2 shoes here, and we release it. This cone, or this hemispherical steel, it will go, it's about 30 pounds, by the way, hemispherically shaped. It will sink into, and we take the reading from here, and there is a correlation between the Kelly ball and the slump, okay? So both of them, they measure workability, which is the very important property for concrete. It's called workability. So, which is the ability of the concrete to be mixed, transported, and finished with the minimum force. So workability, the concrete must be workable. So they came up with the term workability. Workability. So either the slump or the Kelly ball temperature. Also, we measure the temperature, check the temperature of the concrete, because the temperature, as you remember, is going to affect the lateral pressure on the forms. the equations that for lateral pressure on the forms, temperature is part of it. Do you remember the equation? There was one equation way back. We covered it at the beginning of the course, where we can get the lateral pressure on the forms, and temperature is part of it. Temperature is, I can locate it very quick if I can. In chapter 2, these fancy equations that was, here we go. So the temperature, if you remember, T is the temperature. So we have equations where the temperature is part of the calculations to get the lateral pressure or the form pressure as we discussed. So the temperature is very important also. And also the hydration process, it should be done within certain temperature. So the temperature is important in two aspects, or from the two aspects, temperature, because of the hydration, which is a chemical reaction between water and cement, and the lateral pressure on forms. Also, we measure, while the concrete is still fresh, we measure the unit weight, or calculate the unit weight, unit weight, which is gamma concrete, which is the weight over volume. So this is another test we do toward the concrete is fresh. And the air content, we measure the amount of the air, either entrapped air or entrained air. Entrained air or entrapped air. There are two types of air. I talked about it, and I will remind you of something right now, entrapped air. So entrained air and entrapped air. So the air content. And there are two methods, by the way, if you remember from school. One is called the pressure method, pressure, and the other one is called volumetric method. Volumetric. I don't expect that he will ask you about this, but the air content is very important, but I doubt that he will ask you about these two tests, but I would be glad to discuss it when we come back again, when I start teaching again the class in July. But I'm talking about the problem that the modulus of rupture and the F sub C prime. This is while the concrete is wet. When the concrete starts to be hardened, so we are measuring or determining the cylinder test, which is this one here, which is called F sub C prime. Cylinder test. So we cap the cylinder with a sulfur compound, excuse me, and after that we crush it, and this is the shape of the specimen after failure. And we determine what is known as F sub C prime, assuming that the cylinder 6 by 12 or 4 by 8. So the concrete in hardened stage, or after it's hardened, so we can do the compression test. Which is basically the F sub C prime is equal P over A. The 28-day compressive strength. Here is a cylinder after we cap it and we crush it all the way up to failure. So in this case, this is P, which is a failure load, and this is a cross-sectional area. Which is F sub C prime. The second test that we do while the concrete in hardened steel, which is called the beam test, or a flexure test, or we call it also modulus of rupture test. Modulus of rupture test. So the modulus of rupture or the beam test, we have a beam, normally 6 by 6 inch, the cross section 6 by 6, and the span length varies really. Here he gave it you to be 17.5 inch, very not normal. Normally 30 inches is. So if this is L, and we use what is known, so the cross section is 6 by 6, and probably this is what you did in school. We use what is known as the third point loading. Third point loading. Third point loading means that if this is L, we put the load to be delivered like this, where this is L over 3, and this is L over 3, and this is L over 3. And there is a reason behind that, because it used to be center point loading, but they cancel it. So if this is the load that will be delivered by the testing machine, so it is, we have a steel frame like this, where here P over 2, and this is P over 2. Half of the load will go this way. So if you look to the shear moment diagram for this, can you draw it very quick, please? Can you draw it? I know I did this many times, but can you draw the shear moment diagram for this loading situation, just to test your knowledge to see if you still remember? I hope that all of you still remember that. Okay. So if we have the V, which is the shear force, and M is a moment, so half of the load will be here and half the load will be here. So if I go up, positive shear, until I move, and I move horizontal until I hit this load here. So this is P over 2, and this positive shear. Here, there is no shear all the way until I come here at P over 2, and I will go back again to P over 2. So this is negative shear, and this is P over 2, and this is P over 2. This for the shear. The shear is 0 here, by the way. Shear force is 0 in the middle third. But the bending moment, it does exist. And this is what you will see in just a minute in my calculations or my solution. The bending moment, obviously, at both ends are 0. So you will find that the bending moment increases linearly. It's a positive bending moment, by the way, until I reach the maximum here. And after that, it will be constant within the middle third, because the shear is 0. So the slope must be 0. And after that, we'll go back again to this here. So this is a positive bending moment. The question is, how much the maximum bending moment here? This is PL over 6. And the bending moment is constant all the way until the other end, BL over 6, which is, because the reaction here, B over 2, and this is L over 3. So P over 2 times L over 3 will give you PL over 6. And for the beam test, we are using the bending stress formula, which is MC over I, which is indicated in the solution. So let me go to the problem. I'm referring back again to the problem number 23. I don't know why it's shifted like this. There is a space here. He's telling you that third point loading, the one I was talking about. So I can get the modulus of rupture, MOR, or we call it F sub R. ACI code, they call it F sub R, which is MC over I. See this equation. The maximum bending moment is equal PL over 6. Here it is. So it is PL over 6, which is as explained here. And the PL over 6 came from the product of P over 2 times L over 3. PL over 6, where L is the span length. And this is true only for third point loading. Third point loading, where the load is delivered at the 1/3. So the cross section of the beam is 6 by 6. 6 inches by 6 inches. The moment of inertia is BH cubed over 12, as all of you know. If this is B and this is H, in this case B and H are equal, so here it is BH cubed or BD cubed. Let's make it D to match what I use here, BD cubed. And the C is the distance from the neutral axis up to the extreme fiber. This is called C. C. So plug all the numbers and we get 494 psi, pounds per square inch. In fact, the modulus of rupture, which is MOR, or flexure strength of the beam, is very small. Is about 10%, by the way, 10 to 15% of F sub C prime, because concrete is very weak in tension, as all of you know, and very strong in compression. And we use, or we consider the modulus of rupture as a measure for the strength of the concrete under tension. So let me just make sure that I'm writing the page numbers here correctly. So the F sub C prime, which is a compressive strength, which is B over A, and we have the F sub R, which is modulus of rupture, MOR, which is MC over I, the equation. There is another test. Let me show you the picture. It's called splitting tensile strength. We do it for concrete, which is Brazilian test, or the splitting tensile strength, where we put the cylinder on its side and we apply the load this way. And as you can see, after failure, the cylinder has been split into two halves like this. And we take, this is a beam test, by the way. Here it is, a picture for the beam test. Third point loading. And for the splitting tensile strength, they came up with equation, and there is no need to derive that, because F sub CT is equal to P over pi dl, where d is the diameter of the cylinder. This is how we apply this is L, This is the load along the side here through a steel plate to put a steel and piece of plywood, and the cylinder will be split like this into two halves. So the maximum load P, reading from the machine, and diameter D is the diameter of the cylinder, and the L is the length. Those are the three tests that we do. However, ACI, they came up with something that's called empirical formulas. The empirical formulas, EMPIR, sorry, empirical equations or empirical formulas. EMPIRICAL, just to make sure the spelling is correct. Okay, empirical. One of the empirical formulas we can estimate the modulus MOR, by the way, it stands for modulus of rupture. MOR stands for modulus of rupture. Modulus of rupture. So they are saying that if I don't have the capability of testing the concrete in the beam form, okay, I don't have the tools or I don't have the equipment in the field to do this test, can we estimate the modulus of rupture from the compressive strength? So they did a lot of testing and they came up with these empirical formulas. And I believe I used one of them, which is the F sub R is equal to be 7.5 square root of F sub C prime. Which is given in the ACI code. If you go to ACI code, the American code is ACI 318. Is not required as a reference for the AM, but normally I include these equations. I include them in my books just in case. Here it is. This is the equation. The ACI code, just in case. So if I am able to calculate the modulus of rupture, the F sub R, from the MC over I, which I did, MC over I, and we substitute for the moment and for the C and for the I, and we get this 494 PSI. I can use this relationship, which is the empirical formula, where 494 we just calculated. If my math is correct, please let me know if there's any typo or mistake or an error. So in this case, we can get F sub C prime indirectly. So using this empirical formula, so from the beam test, we can estimate or the expected compressive strength. And as you can see, this number here is a huge compared to this number. As I told you, that's about 10 to 15% at the most. The F sub R, the modulus of rupture, is about between 10 to 15% of the F sub C prime. And if you look to the numbers we get here, we got 494 PSI divided by 42 PSI for F sub C prime. You'll find this ratio is maybe within this range. which is about 10% or a little bit more, 494 divided by 4342 divided, and this will give you 11.4%. So it is within the range. And in design, by the way, we ignore this. We ignore the 494. For concrete design, we assuming that the concrete will carry zero tension. So even the 10% up to 15%, we ignore it in design. But we need to calculate this or to estimate this either from the splitting tensile strength, which is Brazilian test, which is 2B over pi dl, or from the beam test, from the Modulus of Rupture. This is helping us for the slabs, especially for the pavement. We need to know the slabs, at what level the cracks will start to occur when we have loads, the tire loads. So this will be compression and this is tension. So the slabs start to crack, and we need to know that. Okay, so this is why we specify the F sub R as one of the requirements for the pavement in order to achieve certain modulus of rupture, so that slabs will not crack, okay, at very high rate or very fast. So I needed to be aware of. So this is the problem number 23. When you print it, please look at it and let me know what types of cements are very important. Type of admixtures also very important that we need to know. For example, here, the type of the cement that is best used for construction in a massive foundation in summer that it in contact with moderate sulfate concentration. So as you know, the type of the cements, we have 5 types, and they are expecting you to know these 5 types: type 1, type 2, type 3, type 4, and type 5. So 5 types of cement, and each type has its own characteristics, and I list them, okay, based on the ASTM. So the type 1, this is a general one, the general, for general purposes. Type 2, as you know, this is for the moderate heat of hydration, heat and moderate sulfate. Sulfate. Number 3, type 3, this is high early strength, fast setting. High early strength, which is a fast setting concrete. We need to fix a roadway and open it next day to the traffic. Type 4, this is high heat of hydration. When I have massive dams, high heat of hydration, because the chemical reaction, which is known as hydration, we need to reduce the amount of the heat because this will cause the concrete to crack. And number 5, this for high sulfate resistance. If the ground or the concrete will be in contact with an area that has high sulfate, so we use type 5. There is I provide also another table in my book, type A and 1A, 1B, all these things. I doubt that he will ask you, but these are the most important um, um, types of cement right now, for the sake of selecting the type of the cement that will be appropriate for a certain application. So I need you to be aware of that. For example, here, moderate sulfate, okay, summer. So probably I selected the answer B, which is cement type 2. So the moderate heat and moderate sulfate. Okay, so in this case, type type 2. Admixtures, also, we cover this in chapter 7 of my book, Admixtures. Those are the additional materials that we added in order to enhance the properties of the concrete. So the admixtures, those are the additive that we added to the concrete before or during mixing, and they are other than the 4 basic ingredients, the coarse aggregate and the fine aggregate and the cement and the water. So they came up with a list of, over years, they came up with these, and I discussed them in my book. One of them is called retarder and air accelerator and air entraining and water reducer admixture. So each one of these admixtures, they are chemicals, by the way. They are formulating these chemicals for us to do certain functions or to perform certain functions other than the normal concrete, because we have unusual condition or unusual situation. So, for example, retarder, this will slow down the setting of the concrete. So during hot weather, and I'm transporting concrete from one location to another, so if the temperature start to go up beyond 90 Fahrenheit, so in this case, we are using retarder to slow down the concrete to be hard. Accelerator is the opposite. Like calcium chloride, we use calcium chloride for as an accelerator, is to increase the setting of the concrete to reduce the time. So air entraining and mixture is one important admixture that we added, and I need you to be aware of that because they might ask you. So air entraining and mixtures, air entraining admixture. This the type of admixture that will create millions of air bubbles into the mix. Air entraining and mixtures. And if you remember the curve, let me remind you of the curve and try to remember this relationship very well, because so if you look to the x-axis, which is the water cement ratio, this is the water cement, how many pounds of water over how many pounds of cement, or sometimes we express this how many gallons of water per a sack of cement. And you know, a sack of cement, as all of you know, it weighs 94 pounds. And a gallon of water, we take it as 8.34 pounds per gallon of water. So the x-axis is the water cement ratio. It can go as low as 0.30 here, and it can go as high as 0.7. This is very low water cement ratio. So there are two curves Oh, I should mention the y-axis is the strength, which is F sub C prime, which is B over A, which is from the cylinder test. Or only one load. It's distributed over the entire, so it's use only one load, P over A. So one of them is for air entraining concrete and one for non-air. This is a non-air concrete. And this is the air entrained concrete. Air entrained. So for any given water cement ratio, you will find that we are getting lower strength for any water cement ratio here, whatever the number is, 0.4. For non-air, I'm getting higher strength versus the number I'm getting from here. Because the strength is increasing this way. This famous graph, famous relationship or graph is, so by adding the air entraining and mixture, this chemical, when we add it, it will create millions of microscopic air bubbles, voids. And these bubbles, by the way, they have a certain range of diameters. I believe I mentioned this in one of my questions, if I'm not mistaken, unless I get rid of it. No, here it is, question number 11. But before number 11, number 10, heavy sulfate. So if you have a foundation that is going to be exposed to heavy sulfate, obviously type 5, which is answer D. We just mentioned it. So the typical size of air voids produced by air entering admixtures is normally 0.01 millimeter, 0.1 millimeter, 1 millimeter. They found that after the microscopic location or determining that it is less than 1 millimeter. So probably I will combine these two answers together as answer D. So it is very, very microscopic. So what will be the effect of the air? Air entraining admixture, these microscopic or these millions of air bubbles into the mix. I am losing strength. For any given water cement ratio, I am having lower strength. So strength will go down. But workability will go up, will be more workable because these air bubbles like a ball bearing, so it will go up. Durability, which is the resistance of loads and environmental conditions, will go up. Modulus of elasticity, which is E sub C, this will go down. What about segregation? Segregation, which is the separation of the, this will go down. What about bleeding? Bleeding, this is the result of the segregation or the outcome of segregation. Okay, when you have a mix, let me draw something here, and this is the member, whatever the member is. If segregation occurs, segregation means the settlement of the coarse aggregate at the bottom of the member. Segregation, you will find that the coarse aggregate, the big particles, is settled at the bottom of the member. And this is a serious issue, segregation. So this will force a thin film of water to be in the top, which is called the bleeding. A bleeding. And this is a serious issue because this water, when it migrates to the surface of the concrete, it will evaporate, and the chemical reaction between water and cement will not be completed, and this will reduce the strength. So segregation will go down and the bleeding will go down, less bleeding. So if we look to this question here, excuse me, question number 12, the air entraining admixtures will decrease all of the following except compressive strength will go down, segregation will go down, which is better, bleeding will go down. The one is going to go up is durability. Did I say it's up here or not? Durability, here it is. Durability. It will increase. What is durability? Is the resistance of loads and mainly environmental conditions, especially freezing and thawing. When we have concrete in the northern states, any water entrapped in, it will freeze during winter or during the cold weather, and when water freezes, the volume will increase, as you know, and will create some kind of cracks. So in order to increase the durability, which will make the concrete durable to resist the environmental and loads, but environmental. So we are using air entraining admixtures, and you will find this is the answer here. So air entraining admixtures will decrease strength, segregation, but durability, which is resistant, here it is. I try to answer and include all the things that in my head, will increase, and this is the main reason for adding intermediate to freezing and thawing cycles. So we need to be aware of that. Let's take a few minutes to break because I need to, let's take, since we are almost right now 6:20, let's take a few minutes to break and come back, please. Thank you very much. Right now 6:20, 6:30 will be fine. Thank you. Okay, welcome back, everybody. Just before I forget, I was planning, but I didn't get a chance. There is one chapter, materials. One chapter in the FE book. I have FE civil book. Is not done yet, but this is a chapter 9. It's a very good chapter. I prepared it about how many pages? Um, 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 about 71 pages. It does have a lot of the stuff I talked about it today. Um, it's very um, uh, good material. I'll try to locate the PDF of this and send it to all of you to help you. So if you don't have my textbook or textbooks, this I think will help you a lot with portion of the materials, not the entire portion of the material. So I try to remember to send this to you. Hopefully I can. I'm sorry that I'm extremely behind because nobody is in the office helping me. Everybody is, because of this coronavirus, everybody is working from home and working from home. There is a lot of limitations. So forgive me because of this. Um, try to do my best here. Okay, let us go back to the, but I will do my best to, some of you, I believe they would like to talk about something or raise the hand. Probably have a question for me. I have no problem with that. Let us hear the question from um, uh, um, um, who has a question for me. Here we go. Okay. From Texas. Hi, Anna. How are you? Can you hear me? Hello? Do you have a question for me? Let me unmute it again. Okay, you raise your hand one more time. Okay, here we go. Oh, I tried to get, for some reason, I am not able to unmute you. It did work and after that disappeared. I don't know why. Let me, if you can write the question, I really appreciate that. But for some reason, I am not able to unmute you, Anna. And I hope that I pronounce your name correctly. I know you are from Texas, to the best of my recollection. So I really appreciate if you can write the question. I will be glad to answer the question if and if I'm able to unmute you, I will. Let me try one more time because you raise your hand, and after that I heard something on the background and disappeared. Still your hand is still up, and okay. Forgive me for that because I'm not able to unmute you for some reason. Let me, because I can unmute a lot of engineers. Yeah, I can unmute everybody except you. I don't know why. For some reason, I have no idea why, but I can mute a lot of other engineers. Yeah, I can do all this, but yours specifically, for some reason, unless you are on a phone, maybe, I don't know. No, I can unmute almost everybody except you. Forgive me for that. So please write the question and I will be glad, or you can email it to me and I will be glad to address it in our next meeting. If you have a specific topic or a specific section that needs to be addressed or to be covered. The discussion about air entraining and mixture, I believe I did address all what I believe that you need to know. Another thing related to concrete, which is MSA, the maximum size aggregate. As you know, the aggregate size, it does have many factors that will affect the strength of the concrete. So the coarse aggregate, these big particles, either crushed or natural, so the size of the aggregate is very important, and they came up what is known as MSA, maximum size aggregate. In fact, in the chapter, let me see if I have it here, of the FE book, I might have a picture. Let me see if I have it or not. Yeah, I do have a picture. For example, it's not available in my civil book. A picture for the requirements of the maximum size of the aggregate. So, and let me draw it because probably the picture is not very clear, but I needed to remember the 1/3 and 1/5 and the 3/4. Uh, 1/3, the slab thickness, and 1/5 the narrowest dimension between forms, and the 3/4 a clear spacing between bars. And I will translate this into English: clear spacing between bars. So let me translate this into English. So they are telling us, or the ACI, they are saying, if you do have a concrete slab and the slab has a thickness T, slab on grade or any kind of slab, so the maximum size aggregate MSA should be less than or equal 1/3 T. So for example, if this is 7-inch slab thickness, so I will take the maximum size 1/3 of the 7 inches. This is the maximum size aggregate permissible to be used for this mixture. So the size of the aggregate, it should not exceed the 1/3. This is if you have a slab like this, slab thickness, or this is a 1/3. The 1/5, this is a 1/5 narrowest dimension between forms. What does it mean? So this case number 1. And case number 2, it's a 1/5 narrowest dimension between forms. So if you do have like a retaining wall, let me get another marker here. a retaining wall, you are building this retaining wall. And you put the forms. So the maximum size, and the concrete will be here. So this is the narrowest dimension between forms. So we take 1/5. Or if I have, like in our case, the problem, we have the concrete beam, and I said that it is 12-inch wide by 16-inch deep, or the depth 16-inch, and the number 8 bar or number 8 bars are required, and they are 3 inches on center. Let's assume that only two bars to make it easy for illustration. So this is number 8. Number 8. And they are 3 inches on center. So in a situation like this, I will test, because I'm expecting that some forms will be here and some forms will be here. Okay. And obviously the bottom. So this is the dimension between the forms. So I am applying the 1/5. And this is 12 inches. So the MSA should not exceed that. So this will give you about 2.4 inches. This is one criteria. The third criteria, the 3/4. 3/4 of the clear spacing between rebars. So right now, I know number 8 is at 1 inch diameter. As you know, the diameter is equal 1 inch. So from center to center, 3 inches. That means that the clear spacing here is what? Is 2 inches, which is 3 inches minus half of the bar diameter here, so 1 inch. So this will be 2 inches. So if I apply the 3/4, will be 3/4 of the 3 inches minus the 1 inch, which is half of the diameter from each bar. This will give me the clear spacing, and this will give you 6/4, which will give you 1.5 inches. So obviously this will control the design. So, and this is why you will find the solution here. I have the 2.4, which is the maximum size aggregate, is the smaller of the two, the 1/5 and the 3/4. So the 3/4 of the clear spacing, so the 1.5 inch will govern, and this is why we selected the answer C. And the reason that the ACI code, the ACI code put these 3 requirements to ensure that we do have enough strength by number 1, uniformity or homogeneity. So I don't like to have a big piece of aggregate to come and stuck here. If the the spacing here is 2 inches only. I don't like to have a piece of aggregate to come and stuck and prevent the concrete to be surrounding the rebars. So in order to ensure that, we need to make sure that the maximum size aggregate MSA is between these 3 limits. And when you receive the mini exam, as I call it, mini exam number 5, and if you have any question, you are very welcome to let me know. Okay. So the one item also I needed to be aware of. So this 3 criteria by the ACI code is set, which is the 1/3 and 1/5 and the 3/4. Please pay attention to this. They might ask you something related to this, or the problem number 14. We have something is called FM, finest modulus for sand, and the finest modulus for sand, as defined by the code or by the ASTM. In fact, the ASTM, it has a very fancy definition. The finest modulus, the FM, is the cumulative percentage retained on standard safe divided by 100. And if I remember correctly, there is a problem in my book at the beginning of the chapter. Is talking about the finest modulus for sand, maybe, or yeah, here it is, FM, the finest modulus, where you have the percentage retained on the sieves here, number 4, number 8, 16, 30, 50, 100. So what we do, we take these percentages that they are retained from the sieve analysis, and we generate a column is called cumulative. And the cumulative, basically you are adding the first number, take this, add it to this, will give you, and so on. Is additive or cumulative, as we call it. So and after you get the sum, you divide it by 100, because this is a definition. This is a definition for is a cumulative percentage by weight retained on safes divided by 100. And this finest modulus, the FM, per ASTM, by the way, this ASTM, the American Society for Testing and Materials, it does have a range between 2.3 and 3.1. So when we test sand in the lab, if the finest modulus for the sand that delivered to the job site is not falling between these limits, we can reject the sand easily, because it doesn't meet the requirements. The degradation requirement for sand, it should be met, otherwise it's not going to produce the concrete that we are looking for. Make sense? So I have 2.3 and the 3.1. I need you to be aware that he gave you 3 samples, 1 2.4, 2.6, and the 3, all of them within the range. And here it is, the cumulative percentage retained divided by 100. Which of the following statement is correct? Sample 1 is coarser than sample 2. Sample 2 is finer. Start to play with. I need you to remember that the larger the finest modulus, the more the coarser. So this is a coarser, and this is finer. So the smaller the number, the finer the sand, and start to be coarser as the number is going up. And I believe I discussed this in my book somewhere when we talk about mixing concrete. So I need you to be aware of that, that the finer the smaller the number, the finer the sand. Okay. And the testing, problem number 20, that when we generate the stress strain curve, as shown here in the handout that I will send it to you. Let me see if yeah, here it is. The stress strain curve that we generate in the lab, and we should know, by the way, all the parameters and definitions for the stress strain curve, a proportional limit, yield, ultimate, elastic, plastic, and so on. When we do this, we collect data, and I give you some kind of data collected in the lab, load deformation. So normally we do have this kind of specimen, as you remember from school. Let me show it to you. I'm sure this is the specimen that we screw it in the testing machine, and we apply the load. We measure the diameter, and from the diameter we can calculate the area, and after that we do the calculations to calculate the whatever. He gave you load versus deformation, but the deformation is based on the 2-inch gauge length. So the specimen is like this. Sorry, my specimen is not the best specimen in the world. We apply the load like this, tension. So we measure the diameter, and from the diameter we can calculate the area. And also we attach what is known as a mechanical extensometer, some kind of gauge to measure the deformation. It's called mechanical extensometer. Mechanical extensometer or extensometer. So this is the deformation, that delta. And it's asking what is the Young's modulus, modulus of elasticity E. Young's modulus or modulus of elasticity, E is equal sigma over epsilon. So I have a data here, 1,000, 2,000, 4,000. So here double the load, and after the double the load, but as you can see the deformation here and the jump from 7 to 22. Our intention is to determine the modulus of elasticity along the linear portion, which is the slope, this Hooke's law. So this is delta sigma, and this delta epsilon, and the slope of this line is E. So E is equal, call it sigma over epsilon, or delta sigma over delta epsilon, whatever is convenient for you. So by inspection, you will find that I have some kind of linearity here, but after that, it starts to deviate from linearity. Deformation start to increase a lot. So if I took the 2,000 pounds divided by the area, this is sigma is equal P over A, and the area is equal pi r square, or by d square over 4, whatever is convenient to you. Oops, let me move my camera here, I'm sorry. So the diameter is given to be 1/2 inch. So I use a quarter by r square, and this B give me this, how many psi, this sigma. The epsilon, which is a strain, epsilon is equal delta L over L. So delta L, I took the 7.14 times 10 to negative 4, because don't forget the negative 4 here, divided by 2 inches. What is the 2 inches? This is a gauge length. This must be given to you. This is a standard, by the way, gauge length. This according to ASTM E-8. If you go to the American Society for Testing and Materials, E-8, you'll find the gauge length. So the default is 2, unless they give you something different from the problem statement. So in this case, we can say that if I can get the epsilon, so delta L over L, sorry, and this is, I took 7.12 divided by 2, this, divide two numbers, I came up with about 28,620 KSI. So I selected the mass of elasticity to be 29,000 KSI, or 29 million PSI. So the mass of elasticity for steel, as you know, is a fixed number, is 29 million PSI, or 29,000 KSI, whatever is convenient for you. So I use the 29,000. I rounded this and I ended with. So something like that. So you have to make your judgment based on double the load and look to the deformation, because you have to stay within the linear portion. This is the mass of elasticity, okay, which is the slope of the linear portion, as here it is when you receive the notes, or and also available in the other books I have. So you'll find that the linear portion of the stress strain curve, the slope of this linear portion, because you are within the elastic range or elastic stage. So in this case, you can determine the mass of elasticity based on that. So this is something that I need you to be aware of. So I hope that try to do your best. There is a lot of questions here, very interesting questions, and try to do your best. And I included, by the way, no, let me talk about this before I forgot. Problem number 5. When we are mixing concrete as part of the material section, the water that we add plus cement, the water that we add to the mix, it must be having certain properties, okay? And the code is using this language. Let me get it for you very quick. Here we go. When we come to the water, the code, they are saying that as a general rule, the water that is a potable water or a drinkable water and has no pronounced odor or taste is satisfactory for mixing. This is the general rule. However, the ACI code, they allow us to use non-potable water, but there is a catch. To be used, okay, but the loss in strength should not exceed 10%. Okay, so we are not allowed to lose 10% of the strength of the concrete if we use any other source of water other than the potable water. And this is something very, very important. So the 10%, so this must be a potable water. No taste, no odor, all these things. But if the only source available for us non-potable water, the code say that yes. So problem number 5, this is what I meant by that. I showed you the section in my book. This is all this, by the way, I showed you all this in my book, in my Civil Bridge AM. So this is the one that has a bridge here. This nice bridge. Okay. So which I did not invent it. I said that all these are given in codes. I'm not Um, um, so the problem number 5, concrete cylinders made with a questionable water and a pure potable water showed 28-day compressive strength of 37 and 4,000. So the potable water, it gave me F sub C prime of 4,050 psi. This is the potable water. The one is permissible or permitted to potable water. But we use some kind of water that is not potable, questionable. As it gave me 3,700 psi. This is non-potable water. And the question, is this acceptable? Bear the ACI code 318. So we said that if I use non-potable water, I should not lose more than 10%. So 10% of that, first of all, 350. What is the 350? This is the difference between 450 minus 3,700. So there is a difference of 350 psi. So I went down by 350 psi because we used non-potable water. 10% of that, 10% of this is 4 or 5 psi. So I lost something less than the 10%. So it is acceptable. So this why I say yes. Is this water acceptable? Yes. The answer is yes. Because the 10% limit that stated in the code is the criteria for me. Okay, so please look at it. Already I included, I believe, in the previous one, I included something about modulus of toughness. We need to know what a toughness is. Toughness and resilience, all these things. The other problems that listed here, for example, problem number 6, related to horizontal curves, and we talked about that before, I believe, if I'm not mistaken. But try to do your best, and I will be glad to go over these things. Oh yeah. Again, one of you asked me about the, I think, Max. I told you that no, they don't. As far as the combined stresses, it is similar to the problem that's given in the NCEES book, and again we dealt with it as an axial load only, without really combining this one here, because the brace is here is 10 and the load is going to be here, my friend. The load is going to be also is not aligned with it. The load is going to be 8 feet only, and 8 feet and this brace. So it is the same logic that I explained it to you. Because if you're using B over A plus MC over I is going to complicate things, and that's not the what they are asking for. They're asking for the axial load only or the axial stress. So what I showed you, okay, you don't need to go beyond what I did. So in this case, because if you are going to align the load with the brace itself, it's going to create, it's going to combine the stress, and I doubt that he does. It can be solved. It can be solved, but I'm saying that I don't expect that this is what he meant. Look to the NCEES problem, and you'll find that exactly what I said is sufficient. Okay. Let me, and you are very welcome to send an email to me, explain it, but this is what please do your best, and I will do all my best, and I will be glad to. I don't know when will be our next meeting. I know I owe you a period because one time I was not available, So let me see if I have my yeah. So this is 4:18. Oh, we're not going to meet until 5:30. Okay, which is the end of May. I hope that the Corona will be gone by that time, and everybody will be happy and start to go out again and eat and enjoy and uh, and uh, and and uh, and study for the PE. Okay, more. Okay, so tomorrow I will be here. Even I'm extremely busy tonight. I have tons of things to do other than. So tomorrow is a 4:19, transportation from 9 to 12, and the construction from 1 to 4. So I will be here tomorrow again from 9 to 12 for the transportation group, and from 1 to 4, sorry, for the. So if you'd like to come, you are very welcome. If you have any quick question for me, you can email it to me, and I will do my best. Just to avoid what I received a couple of calls while I was teaching. I was teaching surveying this morning until about 4:30, and one engineer, he called, or two of them, they called me, they're asking for the link because they didn't receive any notification. I believe if you did not receive a link, you are still able to join me, because this link is not, this email is not generated by us, generated by the company that I'm using. It's called Citrix company, Citrix. Go to webinar.com. So I don't really involve in this at all. So if you did not receive a notification, even I mark it to send you a notification. Don't hesitate to go to www.johnwebinar.com and enter this. You will be able to join me. That's it. You don't have to receive a notification, because it's only one time enrollment, and that's it. So please do your best, because I hope that the two engineers, they called me because I didn't get a chance to call them. Because I need to start the webinar with you guys. So I would hopefully that and all these are recorded, and also my staff, they are working very hard to get it done, to be loaded on the server. At least you can get access to it if you miss any of the lectures. And please let me know if there is any mistake or typo or error or anything I need to correct. I don't hesitate to do that. I will not hesitate to do that. Okay. Thank you very much for coming today, and enjoy the rest of your day. And please always keep in touch with me and pray for me to stay healthy, and pray for you to stay healthy. And thank you very much again. Good night, everybody. Bye-bye.